the Artemis program is actually the name for our moon program. Artemis was the twin sister of Apollo, so we're billing this as the next generation of the moon missions. And we're going to put the first woman and the first person of color on it. So that's part of the genesis of the name Artemis. So with that, the Human Research Program, our whole... Okay, so the Human Research Program, our whole job is to understand and characterize and then reduce the risk to the human system for exploration missions. And of course, the moon is going to be a big part of that as we go on the way to Mars. And just pulling up the slides here. It's all set? All right. Okay, so the Human Research Program, we are based at the Johnson Space Center, so that's just down the road here in Houston. We have a lot going on there, so we're calling it the Texas is the nexus and accelerator for human spaceflight going forward. So KSC, that's where we do all the launches for commercial and for NASA. But the Johnson Space Center, that's where we have the astronauts. This is where we have our space station program, and I'll go through the other programs that we have. But lots going on right here in the Houston area. There's about 11,000 employees, 3,000 civil servants. But you can see the Mission Control Centers in Clear Lake, Ellington Field, where we have the T-38s where the astronauts train on. We have a training facility for the astronauts. We also have the Neutral Buoyancy Laboratory. That's where we do the spacewalk training. They put on their spacesuits, and it's all underwater, and they're neutrally balanced. So it feels exactly like, or close to, it's a simulation of microgravity. Lots of laboratories, including our food laboratory. And then we also do, part of JSC is also out in New Mexico at the White Sands Test Facility, where we do a lot of the rocket propulsion testing. So, as I mentioned, we have a lot going on at the Johnson Space Center. When I came, we were just doing the space shuttle, and we're just getting ready for the International Space Station, which launched in the 2000s. Since then, you probably are aware of the Commercial Crew program. So if you, just 2 days, or maybe it was this morning, I think, we launched Crew 6 to the International Space Station. So that was SpaceX. Before the Commercial Crew program, it was pretty much all access to space was done by the government. But now we're pivoting, and we have commercial providers, including SpaceX, and Boeing will be launching here soon our astronauts to the space station. So the space station, as I mentioned, has been a program since the 90s, and it's been flying since 2000. We're now looking at the next generation. It's not going to last forever, so we're building a commercial LEO, we're calling it commercial LEO orbit or destinations. And so these will be commercial space stations as well, and that program is at the Johnson Space Center, managed there. The Orion program, this is our exploration, the capsule that will take our crew members to the moon and back. For those of you that saw the Artemis I launch, that was the demonstration of this. The next one will have 4 people on it, and that crew will be named here in the next few months. The Human Landing System, that's the actual vehicle that will take the crew members from orbit, or moon orbit, or docking with Orion and take them to the moon. There's another program called CLPS, Commercial Lunar Payload Services. This is managed at JSC as well. These are commercial providers that can take one of your payloads and take them to the moon for research or commercial purposes. We're also retiring our spacesuits. So we've put out a commercial competition, and we have 2 providers that are building the next generation of spacesuits, both for the space station and for lunar exploration. The Gateway, as we talk about that is the space station that will be going around the moon and allow access to all locations of the moon. And then all of this is under the umbrella of a Moon to Mars program. So everything we're doing on the moon is to get us ready to go on a Mars mission. And at the center of all of this is the human. That's the keystone of the Johnson Space Center. We're focused on the human and human spaceflight. So as JPL takes robotic missions, ours is really centered on the human. And that's where the Human Research Program comes into play. We enable space exploration beyond low Earth orbit by reducing the risk to human health and performance. So NASA is largely an engineering organization. With our team of scientists and medical doctors, we're very deliberate about using the language of engineers in this organization. So part of that is identifying what the hazards are of human spaceflight. And so we've identified 5 main ones. Space radiation, which it's very different on the way to Mars than it is on the space station or what we saw on the space shuttle, because you're outside the Van Allen belt, you don't have the protective magnetosphere. Isolation and confinement, you're very far away from your family and loved ones in a very closed, small environment. Distance from Earth, as we go farther and farther. You know, the space station's only 250 miles away. Their moon's another order of magnitude, and then Mars is much farther. So each one of those is a stepping stone that provides us training and opportunities to learn about how to work farther and farther from Earth. Gravity, or lack thereof, I think maybe I'm just biased, but that's probably the one you think of the most when you go to space, either microgravity or a partial gravity environment. And then hostile closed environment, inside the space station, the atmosphere is different than it is here. You have higher CO2 levels. As we go on different moon missions, the pressures will be different. So those all affect how the human body reacts. So all of these can be taken individually and looked at, but really as we go to Mars, these will be integrated, and these are the hazards we looked at. So we represent those here on this chart in the upper left corner. That is the isolated environment. The next one is the distance from Earth, and then radiation's on the bottom. In the middle, you have the different gravity environments, and then the hostile closed environment is on the, I guess, your far right. So we've taken those hazards and we've decomposed them into human health risks. And so those are depicted here. So for example, for the isolation, you have behavioral and health conditions and how you're psychologically going to be adapted to being in isolation for a period of time away from friends and family with delayed communication. Distance from Earth, we start worrying about medical capability. You're not close to a hospital. How do you do that autonomously? You have to take your own food with you and your medicines. If we're going to Mars, that food has to last 5 years or even longer than that if we want to pre-position that. The radiation environment, this we start to worry about CNS, your central nervous system effects, or long-term effects of cancer, and then also cardiovascular disease. As we talk about the different gravity environments, so in zero gravity, we've learned there's lots of changes. There are bone loss, muscle loss, your sensory motor adaptation changes. A relatively new risk that we've just found is called the Spaceflight Associated Neuroocular Syndrome. We just call it SANS, so I always have to read it. And so what we've discovered there is, as you go into spaceflight, the gravity isn't pulling your fluids down, so it pools in the upper body and some of it in your head as well. So with that pressure, we've seen changes in the eyes and in some of the eye function. So some of the astronauts come back that had previously worn glasses, now they don't need them, or they've come back and they do need glasses. For many of the astronauts, this is reversible, and it just, as you readapt to Earth, it comes back to normal. For some astronauts, they don't get this syndrome at all, and for some of them, it does produce lasting effects. So that's another theme, is that the human system is probably the most variable system that we'll launch into space. You know, as we test vehicles, you can test a vehicle to failure. You can understand how it's going to fail. But the human body, we're not allowed to test them to failure. So there's lots of variability, and we have to put limits on what we can do. But each human is very different, both physiologically and psychologically. So that's one of the challenges that we have to deal with. And then as we move over to the hostile closed environment, this is where we see the different environments. The higher CO2, your immune system has changed. You have a different microbiome in this area. So understanding what those changes are, understanding if they're bad or if it's just adaptation that really won't cause any harm, that's really the drive of the human research program. So as we look to the moon mission, we take into account all those different hazards and look at the different risks and look at them through the lens of a moon mission. what we call them a design reference mission, or a DRM. So for example, a standard moon mission, once we're up and flying, you'll probably take 3 or 4 days to get there. You might dock with the gateway, flying around the moon, go down to the moon, spend maybe 30 days there, and come back. So it's a relatively short mission if you compare it to a Mars mission, but compared to the ISS, it does have more hazards. So we look at all of these risks through that lens, and we score them, high, medium, low, or as you see here, red, yellow, and green, to help determine from a human research program and from our different vehicle systems, where do we put investments? Where do we have to study and use our resources to reduce these risks? So you can see for the moon mission, we have lots of green risks, things that we understand. So for food, for example, right now we have 6-month missions on the ISS. That's kind of the typical mission. And the astronauts, they like the food. We're able to keep it very safe for them. And then also the physiology, the biochemical nutrition, that's all very well understood. So that's a green risk. Some of them we're still trying to understand. For example, immune. We do see immune changes. The immune system does seem to be a little compromised there, but we haven't seen is a lot of clinical outcomes. There's some viral shedding that we've seen, and some other clinical outcomes, but it's not something for a moon mission, again, for 30 days that we're going to be that too concerned about. But again, it's yellow. Haven't totally figured out everything going on. We're still studying that. But then we go to the red risks. These are ones where we either just don't have enough data to understand what the risk is, or we don't have a solution. For example, sensory motor alterations. Again, these are changes to your hand-eye coordination, for example. So we have found when astronauts come back from a space station mission, we have them get up and we have them walk. We have them walk with their eyes closed. We have them try to do some functional activities, try to climb up ladders, and you can tell that they're very disoriented. It's a very quick change. It takes them a week or so to come back to normal. I mean, that's an average. Some people come back in 1 day, some take 2 weeks. Again, lots of variability. But you can imagine, as you go to the moon, you're launching from 1 gravity. In 8 minutes, you're in 0 gravity. You're that for 3 or 4 days. And then you're being asked to pilot a vehicle to land on the moon. So then you're going into 1/6 gravity. So lots of changes to the input and output that your neurovestibular system is getting. So again, there's lots of uncertainty there. There's testing we're doing now to characterize that, both to understand it and to provide countermeasures for that. Another one that might not be as evident is human system integration. So what this really means is it's really human factors, it's your training, your procedures. And as I mentioned, you're going to be flying 1 vehicle, the Orion, up to a gateway, and then you're going to get into a Starship, and you're going to be in a suit. At NASA, so we've really pivoted towards a commercial space. And what we want to do is allow for innovation, but at the same time, that presents challenges, because we can't tell SpaceX, you have to make this lever red, and then tell Northrop Grumman the same thing. So how do we make sure that we allow for innovation, but at the same time, we don't have crews that have to go from 1 vehicle where an alarm sounds one way, and then an alarm sounds different on another. So it's how does the human stay functional as you go across the whole architecture on the way to the moon? Whereas in Apollo, it was very, NASA built all the vehicles, and we were able to control all of that. So it's a different paradigm. It's going to allow for a lot of innovation, as you'll see with the SpaceX vehicle, but at the same time, it does present challenges for us. So then, as we set our sights on Mars, we still have the same human health risks, but notably, when you look at the hazards and then the different mission, the design reference mission for Mars, the shortest mission is going to be about 3 years. Again, it's very far from Earth. There's no return. For the space station now, we can get astronauts back in about 2 hours. I think at the moon, it's probably around 6 days we could get them back. Once you burn towards Mars, you're not coming back for 3 years. It's just the orbital mechanics. So you see a lot more red on that. But the good news is we have a lot more time. For the moon, we're planning to go in the next 2 or 3 years. Mars is probably a decade or so away, so it gives us time. Again, that's why we're going to use the moon to understand these risks, the integration of the 5 different hazards, and to reduce those. So when I talk about risks, this is putting it a little bit more in practical terms. So when I talk about a medical condition risk, really what we're asking is, what are the most likely conditions we're going to have? We can't bring a full operating room, but let's figure out what the most likely conditions are and bring the resources for that. For dynamic loads, this is trying to integrate. So when you're landing in a Soyuz or in a Dragon, you have the human, which is interfacing to a suit, which is interfacing to a seat, which is interfacing to a vehicle. And we just don't have a lot of models and experience with that. So those are the things we're trying to integrate and develop. As we go to Mars, we've mentioned, how do you keep a pharmacy? How do you predict what pharmaceuticals you're going to need? How do you know how those are going to degrade and be active? Not just the pharmacy, but how do those, with all the changes in your body, how's the pharmaceutical going to react in your body? Again, medical conditions, as you go farther and farther away, you will likely have a doctor on your mission, but what if the doctor gets sick? How do you provide a medical system that a layperson or an astronaut can operate? And how do you predict what you're going to have and take with you? So these are just some questions that are associated with all the risks. All right, so a little bit about the Human Research Program, and for those of you in engineering, it's really a continuous risk management program. What we do is we look at the evidence we have for human spaceflight, as I mentioned in the previous slides. We look at what risks are associated with that. Then we determine where the gaps are. Where don't we understand this risk? Where do we not have the technology, such as a food system or a medical system? Then that's where the human system, or the Human Research Program comes in. We fund tasks that provide deliverables to either understand the risks or to provide a technology to reduce those. As was mentioned earlier, we are housed at the Johnson Space Center, but we take advantage of the NASA network across the country. So we have 5 different field centers, the Ames Research Center in California, Glenn in Ohio, Langley in Virginia, and the Kennedy Space Center in Florida. But the real driver of all of our work is research institutions. So we have about 200 or 250 research grants out at any one time, and those are spread across, in 2021, there was 34 different states at institutions like Rice, at Texas A&M, where we have principal investigators, where we put out competitive solicitations to say, here's the problem that we need solved, and we need all the smart people that we're working on that. So that is how we get most of our work done in the Human Research Program. So the way we address or attack our problem is we try to do the research in the cheapest place possible, or the most available. And for the most part, that's Earth. It's in your laboratories, it's in analog facilities around the country. Once we think we have a pretty good solution, or we just find that you can't simulate the space environment, that's when we'll take a project to the low Earth orbit, or the ISS currently. And then even more rare will be these Artemis missions. Right now, we're planning about one a year with a crew of 4. So that's not a lot of, subjects, if you will. Those are the steps to Mars. Again, we're trying to understand all the different systems as we go there. And I'll talk a little bit about each of these and what those look like. So the first one I'm going to talk about are analog missions. And when I say analog, this is really looking at probably 1 or maybe 2 of the different hazards, and how can we simulate those best on the Earth. So the first one I'll talk about is isolation and confinement. So what we do is we put teams of people in isolation for up to 8 months or a year. So that's this first one that you'll see is the NEK and SHAPIA. I'll talk first about NEK. So this is a facility at the IBMP, Institute for Biomedical and Medical Problems in Moscow. So what we had was a crew of 6 that went in October of 2021. I'm trying to do it in my head. Yes, 2021. They started their mission, their 8-month mission. So about 4 months into their, well, actually 1 month into the mission, one of their crew members was exercising and broke a bone. They could not set it, so they actually had to remove that crew member. So that was a big square wave that the crew had very early in the mission. Then, of course, 4 months into the mission, February of 2022, there was the conflict in Ukraine. So a lot of the articles in the press that came out were very interesting. They're very sensational. Like, are these the last two Americans that don't know there's a war going on, and Russia's holding these Americans captive in an isolation? Of course, it was not true. They had access to their friends and family, just like our astronauts will on the way to Mars. So they knew what was going on. Of course, they were wondering, is NASA going to pull us? Is they going to take us? Are they going to cut the mission short? Which we didn't. We kept them in there. We, of course, monitored the situation very closely. We have NASA personnel still in Moscow that are working mission control. So we do have a presence there. We have a safe and continuous operations with our Russian partners. But it was really an interesting experiment because on the way to Mars, life is going to happen. There are going to be these world events. So the data coming out of this will be really interesting. The two crew members, we actually had a conference about 2 weeks ago, and they spoke there, and they talked about the mission, what the most difficult parts of it were. And though, yes, it was very stressful, the war that was going on, and they just, didn't have all the information, like most of us didn't. But the most stressful thing was losing that crew member very early on in the mission. And actually, the data that came out of it showed that really changed the dynamic of the whole crew and kind of disrupted them. But it's really great data for us to understand. And that's why we do these missions, these analog missions, to understand when bad things happen, when unplanned things happen, how do crews react? How do the countermeasures that we have actually work or not? So going forward, we've actually built a new analog facility called the CHAPEA, the Crew Health Analog, and that's going to be at the Johnson Space Center. And we actually have a crew of 4 that will be going in July or June of this year and spending an entire year. And this is really looking at the food system. Right now on the space station, we have about 800 choices between all the American food, the Russian food, the Europeans. They have a lot of choices. They also get supply vehicles probably once a month, we'll say, where you get fresh fruit and personal choice items. On the way to Mars, we're not going to have that luxury. We're estimating you'll have about 150 and 200 choices of food, if that. And we still have to figure out those 150 if they can last that long. So what this is doing is really looking at limiting the food that crews have and seeing how they can perform tasks. So those are our long duration isolation and confinement. What we also do in those is we have time delays, so you're not being able to have regular communication. If you have a problem and you call down, it's going to take 20 minutes to get to the mission control and get the answers back. So we're able to simulate that. We're able to simulate off-nominal events. To get ready for these longer missions, excuse me, we do shorter missions, and we do this in our HERA, which is the Human Exploration Research Analog. And again, this is at JSC as well. You see a picture of it. We do 4 campaigns. We'll do 1 campaign with 4 missions, and there's 4 crew members. So to help to get enough subjects, that's what we use this for. So in any campaign, you have 16 data points, and these we're able to modulate the different conditions. A few years ago, we did one where we only let them sleep for 5 hours a night to see how they would react, and some did better than others. We limit the food. We give some of them better food, just throw different things at them. So we get a lot of throughput on this. Again, we take what we learned from that, we package it, we take the best countermeasures or the things that are working, and we put those into the longer missions, such as the CHAPEA or the NEK. One way that we simulate the microgravity is called bed rest. And this is an analog that we've used for probably 40 or 50 years, where you put subjects at 6-degree head down tilt, as you can see a subject here in the upper left, and anywhere from 30 to 90 days. And what this does is it simulates the fluid shift. The fluid does come up to your head. You're not ambulating, so it simulates the muscle loss, the bone loss that you'd see in space. It's not perfect, but it's one of the closest things to microgravity that we do have. I mentioned the new risk that we had with the changes in the eyes. We thought it was weird because we thought it was due to the fluid shift that we had, but we'd never seen this in bed rest before. But what we found was, crew members had pillows. They were able to sit up and eat. So we found when we took that away and we made them keep their head down, you can't sit up to eat, can't sit up to watch TV. Some of the symptoms were actually replicated in this analog. So it was good news for us that we had this ground analog and we didn't have to do everything on the space station. And so now we're able to test countermeasures in that analog. And that's what you see in this picture here. This subject is in 6-degree head down tilt. Excuse me. And she is in a lower body negative pressure device. So what this does is, even if you're tilted, it takes the fluid through a differential pressure and pulls it back into your legs. You don't sit in this for a long duration of time, but up to 4 hours, I think we tested it, to see if that reverses some of the effects of microgravity on the eye. So this is actually going on now. The facility we do this in is in Germany. It's at the DLR, the German Space Agency, at their NVHAD facility in Cologne. There's a number of these facilities in the US as well. Another hazard we look at is the isolation, our dangerous isolated environment. So we do this in the Antarctica. So these are winter overs where it's very difficult to get in and out so once you're there, you're there. And so it's an operational environment. So we were able to see that some of the changes that we see there in subjects are very similar to what we see in spaceflight. As I mentioned before, we see the immune system being compromised in spaceflight. We say the same thing in people in the Antarctic. So we're able to take our countermeasures and test them out there as well. Another hazard, as I mentioned, is radiation. So what we do is we have a particle accelerator, or we take part of the particle accelerator beam, and we use that to simulate galactic cosmic radiation. This is a new facility, the Galactic Cosmic Radiation Simulator. We've just put this in the last year. Before this, we were only able to do single beams, like one ion at a time, for forever. So this is really going to help us understand the cancer risk and the other radiation risks, because right now we had this very good experience base for the last 20 years of these single ions, but now as we look at the multiple different ions to see if our radiation models are predictive. And again, we do most of this on rodent models, and then we try to translate that to humans. So a lot of uncertainty there. Again, this is why it'll be very interesting when we have the longer duration missions to see if our models are correlated. And then finally, we do parabolic flights. So these are flights that fly in a parabola, and you get about 20 seconds of microgravity. And so these are ways to test out technologies or do very short physiology experiments. What we haven't done yet is use the new suborbital capabilities that we see in a commercial space. We are definitely looking at those, as those offer between 4 and 5 minutes of microgravity, but those aren't in our portfolio quite yet. All right, so the next step onto Mars is the low Earth orbit. So these, of course, the workhorse for us here was the shuttle, which had up to 2-week missions, but now we have the International Space Station. Crews here typically fly up for 6-month missions. That's the rotation. We have had 5 crew members now that have flown longer than 9 months. So that is awesome for us to understand what is the time course of change. We have a lot of data at the 2 weeks from the shuttle. We understand 6-month pretty well. But as we go to these 3-year missions we're going to see on Mars, are there things that we haven't found? Like I mentioned, in the shuttle mission, we didn't see a lot of these changes to the eyes, but that we have seen on the ISS. As we extend, what are the changes? So we're looking at doing longer and longer duration missions on the ISS to help connect some of those time points. The other very exciting thing for us is the dawn of the commercial space industry. So of course, SpaceX has been flying now. They've been flying our crews, but they're also now flying private citizens. You probably saw the Inspiration 4 mission a few years ago with the first private crew. And now the next mission SpaceX is going to fly is Polaris Dawn. And these are missions that do not dock to the ISS. They're not professional astronauts. Um, but it's really expanding the pool and expanding the access to space. For us, as I mentioned, individual variability is a key factor. So it's really an opportunity for us. The astronauts are very well screened. We pretty much know their their state before they go. This provides us different types of physiologies that might be at different ends of the bell curve that we'd see in the astronauts. So again, it's increasing access to space and it's increasing our subject pool. Axiom is another mission as well, but these are missions to the ISS, but again, completely commercial. We flew Axiom 1 last year. It's on a SpaceX vehicle, but it's the Axiom company, which again it's based here in Houston. And I should mention the group that does that really pioneered this for us is our Translational Research Institute for Space Health. This is it's a cooperative agreement that we put out from the Human Research Program, and it was awarded to Baylor College of Medicine. What they were charged with was finding different pockets of research and different things that just might not be on NASA's radar. So they have found different technologies for us, and they were really the leaders able to work with SpaceX quickly. For us, as the government, we're not quite as nimble as some research institutions and private companies can be. So that's what we really look to them to do. And they were really instrumental in getting us on that first Inspiration 4 mission, helping us build those relationships. SpaceX has the exact same mission or goal that we do. They want to go to Mars with humans and bring them back safely. So the same problems that NASA has, SpaceX has. So establishing these relationships with commercial, understanding what their business models are, where there's overlap between what their goals are and what our goals are, that's critical, but it's not, at least, when I came in 1994, it's not the type of training that I had. So it's really great to see the Institute here and how you're thinking about the space industry and how to foster that, because that is the future and it's something that NASA is really pivoting to. I mentioned earlier, we started to fund the next generation, what happens after the space station. So in commercial, we're trying to commercialize low Earth orbit. We currently have SpaceX and Boeing that are providing transportation. We have other vendors that are coming online, but we do know that the space station will not be there forever. So we're trying to foster this commercial industry in space. And so we have 4 companies currently that are developing their own space stations. We expect these to come online around 2028. Axiom might be coming online a little bit earlier, as they're going to dock to the International Space Station. The rest of these are free flyers. And then finally, the last step as we figure out how to go to Mars is our Artemis program, or our moon program. For those of you that were able to see it, we launched Artemis I, which was a demonstration of how we'll fly around the moon and return crew members. That was launched late last year. And as we build out Artemis, as I mentioned, it's not just NASA going, it's us going with our commercial partners. It's many different vehicles. We'll launch a crew of 4 in the Orion vehicle. We'll either dock right to a human landing system, as you see here, the SpaceX vehicle, or we'll dock to the Gateway, which will be a space station around the moon. We'll have new spacesuits, and then we'll also have commercial deliveries to the moon from our CLIPS program. The interesting thing I find here is if you look at the spacesuits graphic, that was the NASA design reference vehicle. So if you can see the crew members in relation, it's similar to what you saw on the Apollo vehicle. But as we put out the solicitation for going to the moon, we weren't going to do it alone. We wanted to partner with industry. So we tried to not put out as many requirements as NASA would have put out to allow for innovation. And what you see is a very innovative and groundbreaking solution with the human landing system. That's the SpaceX Starship. And again, for scale, you can see the humans at the very bottom of that in relation to what you see in the NASA design reference mission. So again, trying to open up the doors for innovation and seeing what we get. But going back to the Century Motor risk I talked about before. If you can imagine, I mean, if you're piloting, you're going to be sitting way up, you know, it's 50 meters tall after you've been in microgravity, trying to flip this vehicle and try to land it. You know, it's a lot of risks that we're trying to characterize, but that's what the human research program is here to do, is understand that and to help simulate those and buy that risk down. So it's going to be a stair-step approach, but when we go back to the moon, we're going to be there to stay. We're going to build up an infrastructure there, either moon base or rovers, and you'll see this over the next decade. We'll be taking crews there, international crews, commercial crews. It's a very, very exciting time as we build it up and explore the moon. All both for science and also to get ready to understand how we go to Mars and do the exact same thing there. And we can't do this alone. NASA has it's a good budget. It's a very stable budget. Human research program has enjoyed a very stable budget as well, but it's not ever going to, understand all the risks. So what we do is we try to do as much collaboration as possible within NASA. Our international partners are interested in this as well. Domestically, again, as I mentioned earlier, our risks are similar to other people, problems that they're trying to solve. And then really understanding industry and commercial, working with them, understanding their business models, finding where there's synergies, and collaborating with them. So I think this is close to the end. These are just a few examples of how to work with the Human Research Program and NASA. Starting at the top, it's a very typical research grant. That's where you can find the current ones that we have out. As I mentioned, the Translational Research Institute for Space Health, they have different rolling, more innovative, some different types of solicitations that they do. Then there's the COSI, the Center of Excellence for Collaborative Innovation. This group, it puts out challenges such as X Prizes and other challenges, and this helps people that aren't typically associated with NASA. We try to explain our problems very generically to help people that haven't thought of space before. They say, hey, I'm trying to solve that problem for my oil and gas industry, and I can help out NASA. So we try to put problems out there. We try not to be solution owners, we try to be problem owners and explain what our problems are so people can think about them in different ways. And then JSC is really interested in working in being the Center for Human Spaceflight. So we have a new front door. The address is there if you're interested in working with JSC. So this is my information. If you'd like to reach out and collaborate with me, feel free to reach out on LinkedIn. Always interested in figuring out what ideas you have, because we have very big problems. We've been working on it for a long time. We really need your expertise in helping us get there. As I mentioned, it's a very big gap between when we go back to the moon and Mars, and we need all your help with that. So with that, I will be happy to take any questions or comments. So thanks.
The questions I'll check was online. Well, you can come last.
I have a number of questions. I'll just do one and I'll let the people ask questions.
And sorry, David, could you repeat the question too so that people online can hear it once?
Yes. Okay. SpaceX and some of these other private industries, for them to put a space station, can they finance it all themselves, or is the government subsidizing part of what SpaceX does, both with going to Mars or a space station or other endeavors in space, or are they doing completely privately?
So for SpaceX, I'm sorry, the question is how much is the government subsidizing these commercial ventures? And I would say it's very similar to how the aeronautics and airplane industry started, or the commercial airline industry started. I think at the beginning, there was lots of subsidization, but the business models grew as the price points came down, the technologies. It's very similar to this as well. You can see Blue Origin and SpaceX, they are flying their own private missions right now. So Inspiration 4 was fully funded by Jacob Isaacson. I forget his name, but he's also funding the flight for Polaris Dawn. So the free flying missions, yes, but I fully expect for these commercial LEO destinations, the new space stations, we will be an anchor tenant. We will be funding our use of that, but they are building their business case currently, and they're going to try to offset that. And that'll be part of, I'm sure, part of the selection criteria is that how much are they going to bring in-kind funding to what we can fund as well. Yes.
How long before we get a spin gravity space station?
So the question was, how long before we get an artificial gravity space station? It's a great question. I have no idea. We did have someone contact us, I forget the name of the company, that's told us it was going to be in 2024, but of course that isn't going to happen. But that's artificial gravity at NASA has come in waves and out of favor. It's a tremendous engineering challenge if you wanted to spin a vehicle and go. It's also a challenge for the human as well. It's not as easy if you have especially a short arm centrifuge. There's lots of Coriolis effects. Coriolis, thank you. And then the longer ones, it's harder. So I think it'll be a long time before we see that, but I have no idea.
So just on that topic before we come to you, Adam, is Sarah Mitron saying that there is an SBIR, Small Business Innovation Research Award for an artificial gravity commercial station. And also NIAC, which is NASA Innovation Advanced Concepts, sometimes puts out for this. There are far more ideas out there for what we should be doing and could be doing than there is resources to do them. And on top of everything, in terms of all the safety stuff that David has to worry about, it's a real challenge to get all of those pieces together. But the point is, I think, from my perspective, is the doors are open for these ideas. And now there's private money, and as long as we can do the safety things, that's the kind of thing that NASA is keen to support. Our last speaker was Steve Rader, talking about some of these bigger ideas. And then just, pardon Adam, but Sarah also asked a question, which bone was broken at the NEK analog mission? We shouldn't ask whose it was, but at least which bone?
Yeah, it was, I don't know the bone name, it was the arm, and the worst part about it is the crew member was exercising. So not only was the bone broken, but we had to take that exercise device out of commission for the entire mission. So, so luckily we had a backup device or a redundant capability. But again, that's what you have to think about is on the way to Mars, if either your system goes down, how are you going to have contingency?
Adam, you had a question.
Yeah, so on the hazards chart, we have the red, yellow, green hazard chart for Moon and Mars. And it looks pretty favorable for Moon. We've got a few reds, quite a few greens. For Mars, for 50-50, do we have targets for how many of those we expect to turn green or away from red before we feel comfortable with the Mars mission? Yes, my job is to turn them all yellow or green before 2039. Do we have real targets? No,
I can actually show you. I didn't put it in this chart. I don't think I have it on this, but it's called the path to risk reduction. So we have all those risks, and you can see them nicely turning from red to yellow to green. But of course, it's research, so you can't ever predict with certainty. But yeah, that's our mission.
My joke is if you see NASA in a date on a slide, one of them's wrong. Linda, you had a question. I'm coming back to the front row in a second, but Linda, you had your hand up. You had your hand up, right?
Yeah, thank
Okay.
you. It's also about the symptoms. I was wondering why, how did you get hypoxia down from red to yellow, since it's found that it causes a lot of disorientation, spatial disorientation.
So the question was, how did we turn hypoxia from red to yellow?
Yes.
And I think the answer is it was never red. I think we understand enough about the engineering controls. So we make sure that we write the standards so your life support or the air system is always in as close to normoxic as possible. If you do go to hypoxic, it's gradual and it's not for that long of a time.
Thank you.
Sure.
Well, let's bounce here and come back up. Mark?
So my question is about the future of food. There's a lot of a lot of energy going into reducing the footprint of agriculture. And I was just curious as to whether the Human Research Program is, or Trish, is looking at the potential of using these microbially produced food sources as a sort of a component of a future exploration class mission.
So the question was, as we look at exploration missions and the food system, are we looking at microbially based food systems? We put out calls for innovative, can you 3D print food? Can you look at these different food sources? I think that's probably further down. I don't see it on the radar for the first Mars mission, but yeah, if you're ever going to stay on Mars for any period of time, we'll definitely have to look at growing your own food or different food sources. So we're not funding anything right now on that, but space biology might be. I'm not sure.
Yeah, food's going to be an issue, so fried Mars bars in space, that's what we're aiming for.
My question is about the STEM workforce and the aerospace economy. So we're already facing a digital divide. Source of that is the lack of broadband availability to some learners, and then the lack of digital skills of some learners. And then with Texas's economy being the 9th largest in the world among countries, we're already successful in terms of business, but there's a huge gap in the ability of the availability of skilled workers to match the jobs that are already out there. How is NASA serving as a convener of business and industry to help solve that ecosystem problem, maybe across the healthcare or the university system? How does NASA bring the ecosystem together to help solve the workforce problem?
Sure. To summarize the question is, how is NASA helping the gap between the STEM, our education, and the needs of industry and government? Summarize. I think the biggest thing that NASA does is it serves to inspire the next generation. We get people into STEM. It's definitely one of our key competencies is that we want to inspire the next generation. Even now, it was going to be a gap for NASA when it was just NASA, but now we have people coming out there's SpaceX, there's Axiom, Blue Origin, Sierra Nevada. I mean, it's just exploding, and there is, if you look online, the number of jobs that aren't filled and trying to fill that, it is a gap. It's still going to be a problem. So yeah, we come out, we talk at universities, we do education programs because we do see that. Actually, the Human Research Program, if you want to look up the SHINE program, SHIN, Human Research Program, it's educating how to do radiation research. It's a very niche market, and we see that coming. So we try to get out ahead of that, but yeah, it's definitely an issue, and hopefully it gets better.
And to speak for our sponsor, one of the key things that we've been trying to do with the Houston Spaceport is support these commercial companies, and what they really need is, obviously they need engineers and so on, but they really need technicians. They really need to touch labor, and that could be young people coming straight out of high school, going to the spaceport, and this is some great stories coming out, working on something that's going to be on the moon in the next 6 months, and so that really drives them. They start thinking about wanting to go to college and becoming, partners with NASA, or maybe eventually working at NASA. So it's a slow process, but I think with the commercial entities and the needs, the basic needs that they have, someone who can, turn a screwdriver, that's what's starting to happen. I'm facing the same issue in talking to the Scottish government and what they're trying to do with their space industry. Talents and skills is the future, and Houston needs to be at the center of that in terms of, and again, it's not all about being an astronaut or being a PhD engineer. It's about this whole range of skills that we need to come through, you know. You don't want me to try and fix anything in your house. Hi, David again.
Seems like radiation is just a major, major, major problem. And for me, I don't see a real immediate solutions, because if you talk about shielding, that's almost against space flight, because you want to make things as light as possible. What do you see? Are we going to be able to solve the radiation problem for human space exploration?
I mean, the big investment is going to be on the Earth. You know, we're going to better understand how to test for it, diagnose it early, cure it. That's really the big investment, and that's how we're going to solve it. We are definitely looking at the individual variability, you know, figure out, are there biomarkers that make you more susceptible? What countermeasures can we do? But you're right, we're not going to shield the vehicle anymore. We might be able to get a better propulsion system to get us there faster. So once you're on the planet, you have more protection. But you know, we're watching what's going on in industry. We actually just put out, just a side note on that, through the Steve Rader organization, a call for like, what are the best ways to diagnose early cancer? And the one that blew my mind that came back are these nematodes, or little small worms that can actually smell cancer, like very specific. Like you put nematodes in urine, and they swim towards it if you have cancer. So it can tell you that you have cancer, but it doesn't really tell you what's kind. So it's really looking at these innovative things that are going to, I think, help us with that risk.
Glad that's an external process.
Right.
Keep your hand up for a second.
So with the International Space Station being decommissioned 2031, I was wondering where the resources and focus is planned to be shifted towards for at least human research once we no longer have that facility.
Yeah, so the question was, once we lose this fabulous facility that we have in the ISS, where are we going to shift our research to? And really, it's those commercial LEO destinations. It's the commercial platforms where we're going to be an anchor tenant. We're hoping they're flying by 2028. Again, I put a date on there. We'll see. So there is some overlap, so we can transition to those and then move on. And then also, it's the Artemis program. It won't be as much throughput, but it will be you know, a more analogous environment to what we'll see on Mars.
So where do the Cypher experiments fall into all this? And if they don't, how come it was just recently instituted?
Was the question about Cypher?
Yes.
Okay. So the question was about our experiment called Cypher. And Cypher it's an integrated complement of 14 experiments that looks across all of physiology and psychology. It's the most complicated experiment we've ever done on the space station. What it was designed to do was look at 6 weeks of spaceflight, 6 months, and then a year. So the two main things out of it is really to tease out what are those time course changes, but really look at integrated physiology. Right now, as part of human research, you have to have crew consent. So we pitch compliments to the crews. You know, some will pick, I want to do a bone study and a psychology study. And another one will do, I want to do a muscle study. So now that we have, and we see the end of space station, we realize we really need to use this the best way possible. So we put together this huge experiment. It's a lot to ask of the crews, but they're signing up for it. And so that is going to really help connect the dots on not only whether the time course changes, but what's those individual variability. Changes in immune, are those correlated to changes in bone, and really being able to look across physiology and psychology. So we're very excited about that. Very impressed that you know about that.
Oh, sorry, yeah. Sarvesh, I've been up for a long time today. Sorry, Sarvesh. So Sarvesh, please.
Yeah, I have two quick questions. One, you kind of mentioned that kind of predicting what medical complications would arise during the trip and what medications to bring for that is an issue. Is that as big of an issue with Starship as the HLS? There's a lot more space. Does that kind of solve that problem, at least just for the moon, a little bit easier for you?
Yeah, so the question was, when I mentioned that we'd have a problem with picking what medical capabilities should we bring, does that get solved with the Starship with its incredible mass and volume that it can take? The answer is it definitely helps, yeah, but I think what we're finding even for these first missions on the moon is the training. So we're having to train a crew to fly an Orion vehicle, a Gateway, an HLS, the spacesuit. They don't have time to train how to use this medical suite. So we still have to make the autonomous procedures, the autonomous capability. And again, it's not going to be all doctors that we're flying, so it is that. So yes, for the mass and volume, it definitely helps us. SpaceX is all in on that, along with the research providing that capability. So, so yeah, it's again, very innovative and something, a square wave that we didn't really predict five years ago.
Asha, did you have a question? Yeah, and then we'll come, so we'll do Asha and then come back.
Yeah, I just wondered if there were going to be any robots accompanying astronauts in the early missions, if they help mitigate something of it.
So the question was, are we going to have robot helpers on these early missions? I don't think they're planned for the early missions, but yeah, definitely. Actually, if you remember from the Apollo missions, we had a moon buggy. The new one, the Lunar terrain vehicle, is actually going to be a robot in itself. So it will be able to do autonomous collection as well. So we can either help the astronauts or even when we don't have astronauts on the moon, it can go and do rock collection or other science. And so when the astronauts come back and can help it out. So definitely the future and probably not in the first missions.
In terms of isolation, you talk about isolation as a problem. How successful are the teams that you've trained in handling it and for how long? Like, do they mostly get grumpy and turn out okay, or do they like kill each other?
They definitely don't do the latter, but no, that's the question. And again, it's very, very, very variable from what we see. But that's the great part is you can see the variability. You can see the crews that get along better. You can see the ones that don't. And then you look at what separates the good performing crews versus the non-performing crews, or the ones that just don't get along. I don't know off the top of my head what those predictors are. I'm not sure we know that answer yet. But for the most part, yeah, you see the spectrum.
We'll do two more questions, and then I'll ask, Alec, do you have a question too? Yeah, so.
Just thinking about I think the phrase you used was analog for these physical experiments here in Earth's environment before you go beyond. Given that every experiment turns out, within standard, right? You accomplish the goal of what the experiment was set out to achieve. How many times do you have to get it right before the crew is ready to take it to outer space?
So the question was, how many analog missions, how many times do we have to get it right before we're ready to go into space? So it's an interesting question because there's a difference between research, what we do, it's really understanding the risks and reducing them versus the operations. Operationally, there are very strict protocols. The astronauts, they have to show that they have these competencies, they do different testing, they do their training, they get through that before they're certified for flight. As we go to exploration, that's part of the research job is to figure out what are these competencies, what do we have to train the crew, and try to transition those into the training protocols for those exploration missions. So I don't have a great answer. It's all on a spectrum. It's how much risk do we want to take, how much risk do we want to understand before we go.
I know you mentioned the kind of systems integration architecture was a big right component, particularly for deep space missions. Do you think with the increasing involvement of private companies, I know you guys have the mock-ups like a Building 9 and FPL, but do you think to keep kind of centralized in JSC, you guys will need contractors to come on site and fabricate things there? Because there's going to be, I know NASA's involved in a lot of stuff that's being used right now, but private contractors start to build more and more components kind of on their own and on their own side. Do you think maybe they'll be expand that out on site, or JSC will be in place on the spaceport to kind of?
Yeah, we're definitely looking at marketing JSC as being the Center for Human Spaceflight. I know we're partnering with Space Center Houston on some new opportunities for that. But yeah, as we internationalize, I mean, even currently, you know, the crew members, they have to fly to Hawthorne to get some SpaceX training. I know for some of the modules, they fly to international partners to get training. So it'll probably never be all at JSC, but that's definitely what we want to position ourselves for. And we have a good start. We have the capability. We have the personnel that want to do that.
I've got another 5 questions, but I'm going to spare you all. We can talk over dinner. But again, thank you, everyone online for participating, and for those of you in the audience here, and for all the questions. Obviously, especially for the students out there, there's an awful lot to do, right? And you don't have to stick a date on it, but you can maybe put the NASA logo on it. But you know, this is the kind of thing that I think some people don't. I'm just speaking personally now about appreciate the level. We think of Johnson Space Center as, well, there's astronauts and they send them to Florida for the rockets. But all of this work goes on here and elsewhere around the country and the world, specifically so that we can make this happen and happen regularly and bring it back. So it's really, really important. And the budget should be a lot more, even though it's stable. And I think we all realize that. That's why you're here tonight and why you've attended our lectures in the past and hopefully in the future. So thank you, David. And please join me in thanking our speaker. And you know what I say, right? You don't have to go home, but you can stay here. So thank you again.
Thank you all very much. It's a pleasure.